I'm taller. And today I'm going to present you a new tool. It's an approach to spot consensus bugs in large-scale decentralized infrastructures, like blockchains. So when I do this kind of talks, I would like first to fix the stage, setting the ground of decentralized systems. There is this very nice citation about how a decentralized system is, and it is a distributed system in which multiple parties control components of the network, but nobody is fully in control of the whole network. I would like to do a parallelism between Web 2 and Web 3 infrastructures. In Web 2, we are familiar with. We have this kind of paradigm of client-server. And the server is usually under the control of a very big provider, like, for example, Amazon. These guys can give us very reliable and secure infrastructures, ensuring certain guarantees, for example, of high availability, high performance systems at the cost of a centralized service. On the other hand, if we talk about decentralized networks like blockchains, we have autonomous servers that interconnect with each other, and they are governed by a protocol. They provide certain properties like no single point of failure. There is no need for trust anybody to use their service, and nobody's in control of the infrastructure. And this is actually where the problem is, because if you think about a blockchain, right, we have a number of nodes that interconnect with each other. And these nodes can be myself in my house with my laptop running a node on Ethereum, for example, and another big provider like Infura, which is running a lot of nodes with different guarantees. So in such a large deployment, the challenge is how do we ensure the maintainability of the protocol. We do have governance for doing that, but we do not control the infrastructure. And this is what we want, right? The drawback of that is that when we want to test production-ready applications, if you think about, I don't know, bank use cases, financial use cases, we need to do a lot of tests, also on the infrastructure. So we do have the possibility of running the nodes, the test on the nodes. For example, Infura can perform a number of tests on their infrastructure, but they are not testing the underlying protocol. We can test the applications as well. So we build applications on top of the blockchain. We have some techniques like fuzzing, static dynamic analysis. We can do formal verification, but still we are relying on an infrastructure that we cannot control. So what if we want to test consensus bugs? Or what if we want to test decentralized applications that behaves under difficult condition of the network? Well, you could say, hey, Stefano, we do have testnets for that, right? So what is a testnet? A testnet is a parallel network that can be a testnet for Ethereum, for example, that runs in realistic conditions. So we have node runners, again, that decide to engage with a new network that might run the protocol rules of the mainnet, but might not. So the drawback here is that we have discrepancies between realistic mainnets, like Ethereum mainnet, and the testnets. And this is why, the reason why is that sometimes it's very expensive to run testnets. So node providers prefer to run a testnet that is running with a different consensus protocol, for example, or has different conditions. So how do we leverage testnets for running our test use cases? So just for giving you a snapshot of what happened on Ethereum in the last period. So we had a number of testnets. Someone was running a proof-of-work consensus protocol, others were running a proof-of-authority, and others proof-of-stake. So I hope you can read it. This is like the line map of all the testnets that we had on Ethereum. Ropsten was the first one with proof-of-work, and then we moved toward other networks that were leveraging a proof-of-authority, which is, let's say, a consensus protocol that is run by a fixed number of actors that, with a lightweight protocol, propose blocks. All those test nets got somehow deprecated in favor of a proof-of-stake-based solution. But still, we don't have control of the infrastructure. So what we propose is a different approach, leveraging simulation. And the idea is to have a realistic decentralized system that provides also infrastructure control. So the tool is called Havoc tool, and the idea is to deploy simulated networks, leveraging tools like Kubernetes and Docker, but run in a decentralized manner. With this tool, we can distribute the workload according to our needs, and the workload is, let's say, for firing transactions on the network to observe the behavior of the network. And then the cool part is that you can test it according to network issues. So there is a technique called chaos testing that allows to simulate issues at the network level. So you can crash the nodes, you can inject network partitions, and you observe what happened to your workload. So this is a very basic diagram of the flow. You deploy a network with a steady state. You define a workload, you simulate the chaos testing, and then you observe the metrics. So some of the stuff you can do is here summarized. So you can deploy a network of different topologies. You can even deploy nodes that are running different software versions. You can define workloads according to your needs and inject faults. The metrics you can extract are a number of metrics that move from performance metrics and security metrics according to what is of interest. We did a case study. In particular, we tested two testnets, famous testnets of Ethereum, Kovan and Rinkeby, and we compared them with another kind of private network called Quorum that was running a consensus protocol called IBFT. So the first two were running a proof of authority version of the protocol, while Quorum is a BFT-like protocol, very close to classical distributed system theory. What we did, we ran some tests, injecting partitions and clock skews in a network of in a small network of 4 nodes, and deployed some workloads, and we observed what happened at the network level. So I don't want to bother you with diagrams, but the idea is to observe the number of forks that we measured during the test, and also the number of finalized transactions that were emitted. You can see from the vertical dotted red line the start and the end of the adversarial situation in which we had a partition and a network skew. And if you observe on the black line, this is one of the proof of authority networks we tested, we observed that after the partition got resolved, it never returned to a single fork situation. So the network basically forked forever, and nodes got out of sync, breaking consistency of the network. And we observed that also from the capacity of the network to finalize transactions. Of course, during the network issue we had here, it wasn't possible to finalize the majority of transactions, but then, always looking at the black line, we observed that after the partition resolved, the network wasn't able to finalize transaction anymore at the same level of the input rate, that is the green dot line here. So what happened basically is that the network went out of sync. And the result was that some of the transactions got failed and wasn't able to finalize them. So in conclusion, there are some consensus bugs that we cannot spot even if we have testnets on real-world settings. We need control of the infrastructure. The chaos testing technique is a good approach to do that, but we need to do it in a certain deployment scenario in which the network is still decentralized and reproduce realistic environments. And this is more true now that Ethereum is moving, Ethereum and other decentralized systems, they are moving toward a modular architecture in which we have layer 2s, we have layer 1s, we have data availability layers, we have bridges. All this stuff together that gets integrated needs to be tested in a proper way. So thank you for your attention, and happy to answer questions.